today's topic is the Markforged Metal X, but it's really an add-on, kind of an addendum webinar. We want to kind of talk about what's updated in the last 2 years since we started doing this all. So hopefully you enjoy this presentation. My name is Marcus. I live in Oklahoma, and I've been a SolidWorks applications engineer for over a decade at MLC CAD. Now I do a lot of content and events, so across all the different product lines, Markforged, SolidWorks, and Mastercam. On the line with me, I've got Kyle Norman. He's also a jack of many trades, but specifically dives deep into the additive manufacturing and Markforged. So you want to say hi, Kyle?
Hey guys, everybody, welcome. Yeah, thanks, Marcus. I've been with MLC a little bit shorter stint. I've been here 5 years, but been a longtime customer. Been a MLC customer for nearly 20 years, and worked in all kinds of manufacturing, from injection molding, machining, everything, and from aircraft to oil and gas to firearms. So, yeah, thanks for joining us today, guys. I think we've got some neat information. I'm excited to share all these updates with you guys.
Yeah, it's kind of cool. Once we put it all together, we found a lot of really great stuff, and we kind of broke it up into 3 major topics. The first one I want to cover is what is currently possible in 2021. Right? It's 2021. I want my flying car. What is actually happening in the real world, and what is just sort of a cool idea or future tech that is not viable yet? And when you really break it all down, it's kind of nice to know what everybody's doing and kind of some of the differences between the different technologies. A lot of times people gloss over a lot of details, so I thought it was nice to kind of lay it all out about what all the different technologies are and talk honestly about some of the positives and negatives of each.
The dirty little secrets, if you will.
Exactly, yeah. Then we're going to take a little bit closer look at specifically Markforged Metal X and see what has changed. So if you see one of our previous videos or webinars about the Markforged Metal X and how it works, we probably talked a lot about the features that existed then. This is the updates. These are the things that have happened since then, and a lot of them are based on feedback from customers, requests from customers, and just enhancements to the system, which kind of takes us to our last step, which is what we've personally learned so far. Our Metal X system is down there in Dallas with Kyle, and you guys have been throwing out all kinds of parts, right? Benchmark parts. We've done projects along the way, kind of for some of the content, some of the events, but just going through the motion of that many parts, I kind of want to interview Kyle and see what has it been like after 2 years of being effectively an additive metal fabricator. So we'll kind of dig into some of those little lessons and insights a little bit at the end. So as far as metal printing in 2021, there's multiple different approaches, but you can kind of group them all into just a couple of different categories. So the first is directly printing metal. And what I mean by that is you're solidifying the metal as you go. And that generally involves either a high-powered laser or a welder. And you're just simply solidifying the material little by little. I remembered seeing this, something that looked like this, nearly 17, 18 years ago. I saw a company that was doing research in this, kind of laser additive manufacturing processes. And these have been around for a long time, but they tend to be very expensive. And there are some other drawbacks to them, specifically with safety. And so it's still a very viable process, but we'll kind of talk about what is the current technology in that space. And then you've got the sintered metal, and this is kind of what's been booming over the last several years. Sintered metal is a process that takes powdered metal and kind of merges it in an oven. And it's not something that a lot of people are familiar with. It's just not something, you don't go down to the corner fab shop and they've got a CNC machine, a welder, and a sintering process, right? It's just very uncommon for people to see that, but it's used in very high abrasion and high tolerance and precision applications, things like gears. So we're seeing that process in one form or another really being heavily leveraged in kind of the future of what we see with metal printing. And then the last thing, I really wanted to include this for reference, even though, injection molding, investment cast and sand cast processes do not involve printing the metal. You're basically able to use additive manufacturing to make those processes more efficient and potentially more complicated. And so I thought it was worth at least including those in a lot of our discussions as reference to say, well, if this is what you're looking for, this is still a very viable option and maybe a better way to go for you, depending on your situation. For each of those processes, there are different raw materials available, and in fact, they don't all break out exactly in the same way. So you've got loose metal powder, and there's a couple different ways that you can use loose metal powder, whether you bind it selectively with a binder sprayed out of jets, almost like a inkjet printer would print and solidify it, or whether you're doing that laser melting as it goes layer by layer. Loose metal powder, as you can kind of see from that person who's wearing that ventilation system, is a very potentially unsafe material if you don't have all the precautions. So you got explosion-proof facility, you've got to have ventilators and other specialty equipment. But because it's loose metal powder, we tend to see a lot, if not all, of the high volume metal printing is done this way. The Metal X and some of the recent machines that have come out have been using some variation of metal powder that's in a binder when you get it. That means there's no loose powder at all being used. It's all kind of contained in some way. We use filament very much like you would with an extrusion polymer printer. We've seen some that use rods or canisters. The method of binding it and the delivery method really just determines what kind of machine you need and what kind of quality you can achieve. But that's kind of been the big breakthrough in the last couple of years, is a much safer, much lower cost printer that is able to create parts quickly with metal. And then you've got kind of everything else, right? If it's a MIG welder, if it's a lost wax process, etc. We're talking about it because it's worth mentioning, it's worth referencing, but it's not really relevant to direct metal printing. But I did want to kind of keep it in there for comparison purposes. So if you survey the market and you look at all the companies and all the groups claiming metal printing, you can generally group them all into these major categories. And we're going to use these to compare kind of how everything works. So we'll start out with bound metal. That's the Metal X system. That's kind of the new kid on the block, where you have the metal all bound up. You then have the binder jet, which is another relatively new one. And several of them are doing this, and you basically spread out a thin layer of metal powder, spray a binder in there, and it solidifies it into a bit of a delicate part that then would be sintered along a little bit later. Then you have the direct metal laser sintering, which is where you're melting it as you go, but it's again using that metal powder. You have robotic welding, which I know a lot of people talk about online when we do these types of events or we have videos out there. A lot of the comments section say, where's the welder, where's the laser? Lasers are used quite a bit, but the robotic welding is not used as much in actual fabrication, but we're seeing a lot in the MRO space. Then you got the investment casting, kind of the lost wax where you're melting out the part, or sand casting where you're building maybe like a form or something like that, and then pouring in the molten material. Now the last one I wanted to mention is this DIY option, and I'm starting to see with the success of the bound metal category, we're starting to see some companies try to start up kind of a DIY market for this. And we'll talk a little bit about where that's at, but it really is not a viable commercial option at this time. But it's something to keep an eye on. As we get more sophistication in this process, we may be able to start to see a little bit more prevalence there. But for the most part, all of these processes require kind of a built system, kind of prepackaged system from a vendor. So let's start with some of the things that are important to you as a company, such as the volume of parts. How many parts do you need to make? If you've got singles, even dozens, potentially up into the hundreds, that's where you can look at kind of a bound metal part, that low to medium part quantity, and a low to medium batch size. You can make one part, wash it and sinter it, and get it out the door for relatively reasonable amount of price. Whereas anything that uses loose powder, you're going to have to fill the entire bed with that powder, which means you really don't do one or two at a time for the most part without having a lot of waste and a lot of extra time. So what we end up seeing with a lot of them is you want to keep your part volume medium to high, and your batch size kind of has to be a little bit higher. You can do smaller batch sizes, but usually with anything that uses loose powder, that's when you're going to have somebody running that all day, every day, and that's physically their job. Just like a machinist sits at their CNC machine all day long, with a loose metal powder machine, you're going to have higher volume to justify it, and just because of the nature of it. Robotic welding is very low speed. It's just super slow. You're not going to do much volume with that. And then the casting processes, it's really variable on that because it's depending a lot on the foundry and everything else. But along with those quantities that you can expect to push through these machines and the batch sizes that are going to be viable, you also want to look at any material changeover. Not everybody needs to change machines over. Full production machines often never change material, right? They're always just that one material that they run, and you'll buy another machine for a different series of parts in a different material. It's a little easier to change over with a CNC machine, but with a metal printer, a bound metal printer, it's pretty easy. Just change out the spool and you can run a completely different part in no time at all, from stainless steel to Inconel to tool steel to copper. Whereas these metal powder machines, you really need to do a full clean out to get everything ready for the next material. Even if it's using things like cartridges and things like that, all of the interior must be cleaned out, and you're talking at least a day, a full working day, in order to do a full changeover of the material. So if you're very consistent on your metals, or you can pick one metal and make it work for everything you do, that's no problem, but it's something to keep in mind. For the strength, we've kind of got a little bit of variation depending on who you're doing it with and how they run their process. But in general, anything that's going to be sintered, like a bound metal part or a binder jet part that's fully sintered, is going to have a density and a strength very similar to a cast part, possibly up to a machined part, depending on some other factors. So if you're replacing a forging with one of these parts, you may be seeing too much of a decrease in strength. Now, the DMLS and the robotic welding, because of those heat affected zones, generally are not even as strong as a casting would be, and porosity starts to become a bit of a problem. You're seeing on the bound metal, you can easily see well above the 99% density of metal. And as you get down further, you start to get into the 95 or 90 or 80%. And then you get down into the casting. And again, of course, that's dependent on that process. Now, one important thing to keep in mind is that you do have the ability to do a sparse fill. That means that you could take the same part and print it on all these different processes, and you would actually use way less material, potentially way less material with a bound metal part printer than you would through any of the other ones. That also, though, means that the strength is going to be degraded. So depending on what you're doing, if you're worried about fatigue cracking or anything else, you don't want to be using a sparse fill, because that creates all kinds of internal intentional voids that would create a potential for crack propagation. The surface finish, surface finish is never going to be great on an additive part. If you need something with any kind of a surface finish, in the micro-inch range, you're going to need to post-process this. But just having a finished part to sort of hold in your hand and have it not cut you and not look ridiculous, most of these are going to have a fairly good surface on the exposed surface wherever the part is. DMLS, we're finding, is not as great, but there's a lot of things that can be done by the vendor to create a really high quality part. Robotic welding really suffers, however, because of simply the nature of welding. Now, not all parts are going to be exposed, in other words, finished by the printer. In every case, except for bound metal, there is going to be somewhere where the metal has to be cut away from the supports. And each material or each process has different reasons for requiring supports, and there's some different information available. So for example, bound metal will have a support, but because you have that ceramic release material in there, you're able to separate that part cleanly. The moment it's out of the oven, you just drop that puppy on the floor, it crumbles where the ceramic is, and it's ready to roll. There's very, very little cleanup and no metal cutting required. With a binder jet, you can get away without support, but not if you plan on doing a full sinter. So there's this is something, and Kyle, we kind of talked about this. There's a difference between sintering it fully to 99% plus density and sintering it to a density of, say, 60 to 70%, and then infiltrating that part. And basically you're creating a part that is a matrix of the base material filled in with either a bronze or brass or copper or something along those lines. I got a part to show you on that. For the DMLS, a lot of times your supports are specifically to act as heat sinks to pull the heat out of the part as it's being printed. So it's not that it needs to be, attached to the bed necessarily for the process, although for accuracy you need it to be connected to. There's just no way to get around that. Now with robotic welding, a lot of times you won't have a cut scar simply because you're welding on to add material to an existing part. So it's kind of an interesting thing there where I guess technically you don't have to cut it away if all you're doing is adding features to existing geometry. And then the last thing I wanted to talk about was a green step. Green is that concept of you have the part formed in terms of bound metal particles, but it's not solidified into a solid metal part. Therefore, it's a little bit like unfired clay, and you can take it and you can sort of sand it, you can cut it, you can engrave your initials on it, you can do whatever you want. And if you're just looking for some aesthetics, or just, that a little extra additional step that doesn't involve hard metal cutting, anything that's bound metal or binder jet does technically have a green step that would give you some chance to do some work on that. We actually have a whole video just on green sanding on our YouTube channel, which is where this presentation will be going when we're done. As far as part cost, unfortunately, nearly all of these processes are using some manner of powdered metal, and that powdered metal has to be made very specifically with very consistent size, and that extra processing step simply adds a lot of cost. That cost has to be also include things like the machine cost, throughput, downtime, waste, lead time, etc. But if you just compare a metal part on a lathe or a CNC machine, or metal shapes, versus anything metal printed, you simply have a much higher cost for the raw material because of that extra processing step. Now, there's some waste involved, but it's important to kind of understand how that waste is handled. So in the case of bound metal parts, we have usually a raft, or at least some kind of a support system that holds the part during the sintering process, that then gets separated. Now, that raft can be recycled, but it can't just be fed back into the machine as new material. That material is going to have to be sent off to be recycled like any other industrial metal. But because you have sparse fill, you could make the same part as any other machine, but with way less metal required to build that solid part. Now, as far as binder jets and DMLS, you're going to have that loose metal powder that can be recycled. So you're going to have to fill up your entire bed up to the height of the tallest part with full up with metal powder, but then that metal powder gets siphoned off and filtered and can be recycled a certain number of times before you're going to have to start looking at maybe discarding that. The supports do have to be thrown away, and again, they cannot be recycled directly into the printer, so that's something to keep in mind. Consumables is something you really got to keep in mind on too. Everything is going to be a little different. Each of the different machines and each of the vendors even have some variation on what those consumables are. And so you want to kind of keep an eye on what those look like. A lot of times those are going to be consumables in form of ceramic release, possibly in some solvent or some cleaning materials. Could be gas, very often is gas for the sintering process or to create an inert environment. But just make sure you're aware of the specific consumables, where you're able to get them, and whether or not they're proprietary in some nature. Infrastructure is also an important thing to keep in mind, and this is going to vary depending on who you are. Starting with the casting process, if you already do investment casting or sand casting, this is a no-brainer. You should be using additive to support those processes. That'll make you so much more efficient and do great things for you. And if you already have those, you already have bandsaws and EDMs and other machines necessary to cut away any supports or any fill runners and stuff like that. So that's going to be super easy. Now, if you don't have a metal shop where you have machines specifically set up to cut metal, specifically hard metal like stainless and tool steel, then you're going to have to think about whether you're going to be willing to buy all of that equipment to go along with it. The bound metal parts do not require any cutting other than any post-processing you might want to do on a CNC, but every other system is going to require some cutaway in order to release the part. Now, in the binder jet, I say yes and no. Again, I'm talking about the infiltrated part versus the solid sintered part. I'm going to show you that here in just a second. But on top of needing additional facility infrastructure for cutting the supports away and any cleanup that needs to be done, you're also going to have safety requirements, floor space requirements, power requirements. Sometimes you're just literally going to have to build out a special facility built for this very purpose. So if you don't want to build out something really big, a bound metal part is definitely a great thing to look at. With the binder jet and the DMLS, the facility requirements are pretty high, and so are the safety requirements. And so you're really going to want to keep an eye on that and make sure you fully understand what's going to be in for every dollar you invest in the piece of equipment. How much are you also going to have to pitch in to get your machine, your facility ready? Again, some companies are going to be ready to go right now, and they can just install it into their existing production floor, and others are really going to have to build up around that. Now, we talk about the support and the metal cutting requirements, and it's really important to know that there's some companies out there that are really glossing over the difference between two different types of finished parts. So the part on the top left here, that's a Metal X part. The surface finish looks a little rough, but that's just the striations at the edge. It's very solid in the middle, but there's a ceramic release layer underneath the part and on top of the raft, and that supports it fully. And even as it shrinks in the oven and does some really, funky things going on there, that raft does a fantastic job of holding everything in place and keeping the dimensions very, very stable through the process of sintering, and then it just releases once it's done. Now on the right is a part that might have been done with DMLS or some other process where the supports are attached. And notice the supports are in the interior hole, they're underneath inside the ribs, they're underneath the overall part. They're kind of all over the place, and you're going to have to go in and clean up and cut away all of those connections on all those support locations. So that's what the metal cutting looks like. If you see a company that claims to be able to do a part like like the part on the bottom left corner, but they claim that supports are not required, they're probably actually talking about infiltrated parts. Infiltrated parts have a 60 to 90% density of, let's say, stainless steel or tool steel, but then they're infiltrated up to 90+% with brass or copper, which is great if you're trying to create a bearing or something like that where you want to impregnate and infiltrate that part. But it is not a full strength, metal part. You're definitely going to see a lot of strength decrease simply because of that process. So if you ever see anybody talking about supports and cutting of supports and things like that, just make sure you really understand and don't do those terms synonymously. Markforged cannot create parts to be infiltrated. They have to be sintered to full density. So that is a limitation of what we can do, but it also means that we can't sort of say you don't need supports here, but you do need them over here. For the cost of the equipment, that's really what the Metal X, did for the market more than anything else, is they brought the cost down by an order of magnitude. You're in the hundreds of thousands range rather than the millions of dollars range for anything involving a loose metal powder. With respect to the number of steps, that's another thing we see a lot of people talk about. They say, well, that seems like a lot of steps. You have to slice in the software the part and then print it and then wash it to debind it, and then you have to sinter it. And that does give you a full lead time, a practical lead time of about 3 days from idea ready to go to part ready to install. And if you compare that to some of these other options, they can at least have the potential to go faster. But what's important to keep in mind is with the binder jet and the DMLS, you have at least as many steps, if not more steps, involved. So in the binder jet, you've got to print it, and it does print much faster because it's that loose metal, but then it has to cure the binder inside the build unit. Then you have to clean the parts out, clean away all the extra material to get it recycled. Then you've got to cut the part out, and then you either have to sinter it or infiltrate it to solidify that. With DMLS, it's much faster, but because you're running high volume, the reality is it's not so much the equipment that's keeping you slowed down, it's really the production volume and the production schedule that you would probably have to work down. But as long as there was nobody in your way and you got your way and you could kind of cut in line and cross everything else, and there was already some material you needed run, it is possible to do it in about a day. Just keep in mind that the reality is going to be a little bit different there. So not a ton of difference between the lead times and the steps. They all require some level of involvement, but we find that our steps are really kind of set it and forget it, as opposed to have very active steps that involve somebody doing some serious work with some serious equipment. So if you take all this together and you look at each of these different steps and each of these different processes, they really do shake out for different purposes. So bound metal printers, very much like the Metal X, are almost always going to be lower volumes. So that's going to be prototypes, fixtures, small batch production, any kind of a repair operation and maintenance operation where you need a stainless steel part with a decent amount of complexity that normally would have required quite a bit of expensive tooling. You just want to build that part and get it into service right away. That's a great way to do it, but you're not going to take it really high up into full production. There are ways to scale it, but keep in mind, it is not designed to be running hundreds and hundreds of parts. If you need to do that, you've got to bite the bullet and go up into the powdered metal. So with both binder jet and DMLS, you're talking about a serious investment, millions of dollars to get going, but it will do everything that the Metal X would do. So it's going to do prototypes and fixtures and small batch, but it's also going to do full production. And so anytime you see aircraft companies that are doing full production, fuel injectors for jet engines, it's generally being done through a powdered metal part. The robotic welding, we actually see that a lot in repair and rebuild, especially with companies that maybe are taking wear parts, really large wear parts, and they'll build the material back up and fill in any damage or any repair or any wear surfaces and then machine it back down to its original spec. So all they have to do is rebuild the wear surfaces. The rest of the part is simply stays the same. The casting is going to be done by companies that have the ability to do casting. I've got a great company that's local here that's a SolidWorks user that bought a different machine because they have a great relationship with the casting company. So they got a part that made wax molds, and they would just ship those wax molds over, and they'd get them cast within a day. So for a company like that, they are able to take advantage of those capabilities. With DIY, you're really looking at this in terms of research only. There are companies out there that sell you material that looks very much like the Metal X filaments. It's got bound metal. The problem is you have to figure out how to get it through a machine, which is not easy. If it was easy, people would have been doing it by now. So it's hard to get a good quality print. After you get a good quality print, it's hard to get the sintering process done. It's a very long, drawn-out process involving many steps, and it's got to be done very precisely. Otherwise, you will not fully solidify the part, or you might melt the part, depending on the accuracy of your oven. So if you see someone out there that says they're going to do a DIY metal printing, they're really, really stretching right now. Now, that's not to say that that's not going to be very possible in the next few years, but there's just huge gaps in available knowledge and information, and there's just nobody that I've seen doing anything successful that didn't have some kind of a PhD or didn't make this their number one priority, which was just printing parts themselves. So let's talk a little bit about what's changed since release. We've had a lot of stuff improve since the material list was released. We started out with primarily stainless steel and a little bit of tool steel when the Markforged Metal X was released. We've since introduced Inconel, copper, and some additional types of tool steel. Inconel, extraordinarily tough, strong, corrosion resistant. Copper is a very tough material, very hard to machine, great for heat sinks, electronics, welding applications, things like that. We're seeing some really awesome applications for copper. And then the various tool steels, we're starting to see people build bespoke custom CNC tooling and things like that out of these tool steels that are really some fantastic material. They're all using the same release material. They're all going through the same machines. They all have to be sintered one material at a time, but they all can be made on the same machine pretty easily. Another one is the options on the print. For example, the raft, if you don't want to use additional material underneath it for raft, you can just turn raft off and say just print it just by itself. It does kind of drag a little bit on the surface of the center plate, so you definitely have just a tiny little issue with that. But when you're really looking to save a lot of material, or you don't have a lot of accuracy requirements on that bottom face, skipping the raft step is a totally viable option. We've got a smaller layer height option for more accurate parts. We can also do chunkable support. We figured this out pretty quickly when we did parts that had either internal or external threads. The supports themselves created a helix, and that helix could not be separated from the surrounding part. So with chunkable support, it creates little cuts, and it just impregnates various different breakpoints with that ceramic. And so what you got to do is just hit it, and it starts to pull apart all those structures into individual small pieces, rather than it trying to be one solid support block. We also have a couple new ones. Center stability, which is described as maybe sacrificing some of the surface finish, but to create a part that is much more stable in terms of dimensional accuracy after the center, as well as leak resistance, which is a specific way that it prints to make sure that it gets a very tight seal on all ceilings and walls. That way, if you have any internal pressure on the part, there's not going to be the possibility of a very small, included crack or something like that in between the layer lines where it might be able to leak. You have the ability to do solid infill or sparse fill, so you can make the part much lighter weight, or you can make it full solid if you need full strength. And exposed infill means that you can print with the infill visible. A lot of times you might do that for just kind of demonstration purposes, but it's also really nice if you want to kind of expose that sparse fill to fluid or some other kind of a thing. We have variability in the wall thickness on the floors and the walls. That makes a really nice part that would be post-processed on a CNC machine, either a lathe or a mill, because it's got a lot of extra meat there that can be machined away down to the final tolerance. We also have some additional part details. So it used to just be the print, wash, and dry time and the mass. Now we can look at what the part dimensions are, both before it gets printed, after it gets centered, the mass, width, any raft and other support material, total volume, total material cost. You get a lot of great details depending on what specific process parameter you're trying to look at the data for. The processes themselves have been upgraded, so including kind of coming from the software, we have the ability to print a lot faster. There's a lot of improvements in the way that the machine is pushed and the way that it's programmed to be able to get your parts out faster. The estimates on how fast it's going to print, as well as the amount of time it takes to wash and sinter, are more accurate and faster. So some of the major releases, we saw some huge reductions in wash time and sinter time due to ongoing R&D, meaning that they may have figured out they can cut 10 minutes off here and 10 minutes off there and maintain full part quality. They would push that out as an update. And even first generation brand new machines coming off the line are going to run just as fast as a brand new one that you buy today. There's a new turbo center option that allows you to center in a very short amount of time. And then for tool steel, you can actually, at the end of the center process, you can have it do an anneal run, which will anneal it to a much softer material so that you can machine it to its final tolerances before being re-hardened again up to full strength. We have a new printer oven. So that's the Center 2. The Center 2 is a much bigger opening. So the Center 1, the volume was about the size of a loaf of bread inside. And with the Center 2, you have multiple shelves that you can fill parts in so you can get a lot more volume. Or if you have really large, bulky parts, those can go in there and get centered in that center too. And if you have external centering capabilities, you can do that. Just skip the process within our system and get that part solidified elsewhere. The software has been upgraded in some very substantial ways. Blacksmith is a revolution in terms of accuracy and precision. So the way it works is the parts are going to shrink a little bit when they are centered, but they are very predictable. That's why we're able to use centering processes for things like gears and gearboxes, because it's a very predictable shrink. As long as you know what it's going to shrink to, you just back that up, print undeformed, and you'll get exactly what you expect. Well, Blacksmith uses artificial intelligence and scanning to allow you to create a part, print it, scan it, and teach the AI algorithm what it's going to do when that part gets centered. And that AI algorithm then can predict better what the part needs to be shaped in order to get the exact final requirements. So for example, if a part always kind of centers out and it grows by a few thousandths, Blacksmith would be able to capture that and accommodate that and sort of offset it in the centering process. So the exact same part gets more and more accurate every time you run it, and it benefits from other people who run that scanner as well. We have some print farm capabilities to allow you to hook up multiple machines and pieces of equipment. So for example, you may want to get 3 or 4 printers, but then you can use only one wash and possibly 2 centers to put it all together, and the print farm helps you to manage all that queue. And then we have Eiger Enterprise along with the security certifications. So with the security certifications and with Eiger Enterprise, you start to look at some really granular security and permissions across all the different parts and pieces and processes. And you can really be sure that your intellectual property is safe when it's stored inside Eiger. So Kyle, let me bring you back in. First of all, make sure that I didn't say anything too out of turn. How did I do on all that beginning part as far as the state of metal printing and kind of what Markforged has changed since release?
Yeah, I think you've pretty much hit the nail on the head. It has been a learning process. We're still talking about a technology that's really in its infancy. We have learned some very valuable lessons, which brought all of those enhancements that you talked about, right? Some of the things we've learned as far as applications, you really kind of touched on it. The low volume, one-off jigs, tools, fixtures kind of things are really where Markforged Metal X hits the sweet spot. What we've really learned is, hey, this isn't laser centering. We aren't laser centering. We don't do the things that a laser centering machine does, or a infiltrated part. This doesn't fit every application. What we've really learned is, don't try to twist it into those applications that it doesn't really fit. Very early on, we had a lot of people interested in the Metal X with applications that just didn't fit. I think it's really important to note that none of these technologies are a one-size-fits-all for any manufacturer. These have very specific places and very specific things that they do really, really well. And they all excel in different things. The sparse fill is something that we found is very valuable, in that we can create a very light but very, very strong part. So we're seeing the strength capabilities of, say, for example, stainless steel. But when we produce parts, for example, say a robot, we're putting so much less wear on those joints of that machine because we're running a part that is significantly lighter. So you'll see weight characteristics more indicative of aluminum, but you've got the strength of stainless steel. So that has been a That's been a really huge benefit. As far as applications for materials, the stainless steel has really kind of been, the 17.4 has basically been the jack of all trades. It has been a wonderful material. The tool steels work for certain people. We've got customers that are doing punch dies, lots of tooling applications, production line applications for those tool steels. Inconel has been an extremely interesting material. I think we've only scratched the surface on Inconel, and copper probably had the most hype out of any of our materials. And in fact, that's what the watertight feature was developed exactly for. So we've got lots of customers using those as welding probes, lots of cooling applications. And the reality is we're the only one with a pure copper. So most coppers available in the additive world are about a 60% alloy, and we're a pure copper. So it's a really interesting material. It's got some really great applications. Another thing we learned over time was, when you walk into a shop that doesn't use consumable gas, when we're talking about argon or forming type gas, our technical guys have gotten really good at explaining the process of using the gas, especially to the shops that never used that. It was kind of overwhelming for some shops initially. It has turned out to be very simple. And then as far as kind of post processing, definitely one of the things we learned was green sanding is a really simple, really fast process when you really want to clean up the surface finish of your parts. So this allows you, after you go through the debinding process, just with very, very minimal effort, to really clean up that surface finish of that part with just a really light sanding, and you come out with a much, much smoother surface finish in certain areas. So it just depends on what you're trying to accomplish with that. We did discover that bead blasting, tumbling, there's lots of neat things you can do. It's really, really simple things as far as, typically a part we hit with a hand file just to knock any sharp burrs off, and then we'll run through a polishing wheel just to kind of smooth everything up, make it look nice and pretty, and it's as simple as that.
Yeah, I've come from a woodworking background, and so I hadn't really had a lot of experience with metal. And so there's just a handful of things that I know you guys were doing that was really able to create some beautiful parts. And for those of you that have background in finishing metal, that's great. Just wanted to kind of talk about some of the things that we're doing, and that you might want to kind of be ready for if you've never done any kind of metal post processing. It's not overwhelming by any stretch, but they really make some beautiful parts.
Yeah.
Very good. All right. Well, Kyle, I appreciate your help here, kind of providing some perspective. We're going to open it up for questions and see if anybody has anything they want to learn a little bit more about, or have any specific questions about the Metal X process, or just metal printing in general.